Right, but let us start. So the first talk today is by Boris Khoruzhenko, who has already given one talk. So now it's the second talk, and it's nonlinear analog of May-Wigner transition.
Thank you, Leonid.
But not everybody was here for the first talk.
No.
Yeah.
Okay. So for some, it's.
But repeating the talk was not an option.
It's not a sequel.
It's not a sequel, no.
No, it's not.
It's
no.
completely unrelated.
It's not part two.
And you might find that it's unrelated to what you're doing anyway. But there will be some eigenvalues. So thank you very much for giving me this opportunity to talk about joint work with Yan, who is here. It's ongoing project, and I think that we will write it up and submit to archive within 2 weeks. I can promise.
This is the goal.
That's the goal, yeah. But everything is done.
Sorry, Boris, you know what else you are supposed to do?
Oh yeah, preprint here, yes,
Yes.
of course. Yes. That kind of comes first before archive. Yeah, so there's a little a nice calculation which is related to calculation by Robert May, and we just extend his framework, I would say, to from linear settings to non-linear settings. So I would first want to explain what is meant by May-Wigner instability transition, or sometimes in ecology journals it's called May-Wigner theorem. May-Wigner theorem. Right, so kind of in layman's terms, May-Wigner theorem says that complicating matters tends to multiply the number of ways that things can go wrong. That's a fairly obvious statement, and one would wonder why you need a theorem to prove it. But if you think about it, maybe it's not so obvious statement, and especially in the kind of background or the context that Robert May was thinking about it. So he came to this problem, question, thinking about ecology. So in 1950s and 1960s, the prevailing view in theoretical ecology was that if you have an ecosystem, then the more species you have in that system, the more stable it is. And that was, for 20 years, that was more or less like dogma. No one actually tried to challenge it. There were some numerical computations or calculations at the time which looked at a prey-predator model for 2 species. And they found that increasing it to 3 species, you don't get more stability. So it was more or less a lively question, and May was at the time in Princeton, and I think that he was talking a lot to Dyson. So he came with an idea how to take on this problem. So that, of course, May analyzed only a very caricature model. However, his paper proved to be very, very influential. It has a lot of citations, and it changed the view how ecologists would think about the stability question. So in a way that, of course, when May derived that conclusion that more species or more complexity does not bring you stability, of course, many ecologists said immediately that that's a very unrealistic problem. You don't have random interactions, and there was a lot of criticism. But over the time, kind of the main kind of positive things that came out of May paper was that ecologists started to think about generic structures in kind of ecological system and see what kind of structures make ecological systems more stable. So his framework is still popular today. There are papers appearing in Science and Nature which kind of try to adapt May's model to a more realistic system. It also, there is a kind of another development, and his framework is used in game theory and more recently in financial ecosystem. So people are arguing that you don't let things, in banks, you don't let things to evolve at random because then it leads to instability. But there is more substance to what they're doing in kind of finance.
Correct, financial ecosystems. What do you mean?
Yeah, that's applying ideas from ecologists to finance. And I also had a very nice picture of financial ecosystem, what it represents, but I didn't have time to. I'll show you.
Might be, but just the term itself.
It is a term that was coined by Robert May and someone else. Actually,
Does it work?
I read his papers, and the bulk of it is common sense, more or less, but it's always good to refer to a mathematical theorem, because then kind of finance people and banking people would believe you more. But this is exactly, I think that this statement, I took it from Financial Times, because if you want to get your message to people who are minded differently, you try to explain what you do in simple terms. Okay, so that's enough for kind of background, and then now we'll go to some modeling equations. Right, so what May actually did, so his first departure from standard ecology view was that instead of considering one prey, one predator system, or two preys, two predator systems, he considered n prey, n predator system. And of course, generically there are equations, Lotka-Volterra equations, but there are more general equations that describe the evolution of expected number or number of population numbers with time. And this system of equations are differential equations, ordinary differential equations, and they are nonlinear. So of course, nonlinear problem is very difficult to tackle, but if you presume that there is a equilibrium, you can do a neighborhood stability analysis, and this is what May did in his paper. So he considered a system, generic system with n degrees of freedom, and which is kind of defined by a field F or flow. And what he did, he presumes that the point of equilibrium is at 0. You can probably shift it to get it at 0. And then he used Taylor expansion to expand F in the vicinity of equilibrium. So I now want to explain what this parameter mean in May's problem. So that May said that, well, if you have n species without interaction and you have an equilibrium, so if you disturb species from equilibrium, then they come back to equilibrium with some exponential rate. And this is what mu is here. So of course he assumed for simplicity that the rate of damping or relaxation time scale is the same for all n species. Okay, this is maybe not so realistic, but for simplicity that works. And then he said that this matrix B, this is just derivative of F, of components of F. F has n components with respect to species. This is just, it characterizes the strength of interaction between species. And the ecology settings, B actually measures per capita effect of species J on species I. So if you kind of increase population species I, then you see how many. So increase population species J, you'll see how it affects on the population of species Y, and this per capita. Because it is per capita, this matrix B is asymmetric. Think about in ecology, think about population of insects and population of trees. So obviously there are too many insects, and to make an effect on trees, you really need to have too many of them. So this matrix B is asymmetric in ecology setting. So then, of course, it's when you linearize, you have a linear system, and its analysis is very simple. So you just look at the eigenvalues of matrix minus mu plus B. And May said that because the system is complex, he would assume that interactions are random. There is no preference to kind of mutualist or prey-predator, everything is random. And then you are back to a random matrix problem. So if you have this random matrix and you want to see where the negative real part of eigenvalues is. So if the real where real parts of eigenvalues are. So if you have eigenvalues with if you have eigenvalues, all eigenvalues with negative real parts, then the system is stable. And if there is at least one eigenvalue with positive real parts, then the system is unstable. So then he said that there has been a lot of development in random matrix theory, and he referred to Wigner. And using analytic techniques, that's a quote from his paper, developed for treating large random matrices, then B is almost certainly stable if mu divided by alpha square root n is greater than 1, and is stable if mu divided by interaction strength square root n is less than 1. Obviously, from this conclusion, if you increase the number of species, then sooner or later, this becomes less than 1, system becomes unstable.
But Wigner was about the Hermitian matrix.
Yeah, that's what I'm coming to this. So, because it was a paper in Nature, I don't want to criticize May, and maybe he had, the conclusion he arrived is actually the correct one. But he also said that the transition is very sharp, and the width, relative width of transition is 1 divided by third root of n to power squared. And this is characteristic for symmetric matrices, and I think that he is likely to have used Wigner calculations for symmetric matrices. He was aware that matrices are symmetric. But nevertheless, he arrived at the right conclusion. And
here, what you said wrote before, diagonal has to be 0, no, of EJK.
it's on this
It's not
scale, it doesn't
important,
matter.
They do not contribute.
Yeah, they don't contribute. Yeah.
Because the normalization was square root of n. So you can put
I
it
can
at 0.
remove the diagonal.
Yes.
Okay.
It doesn't matter. And I will kind of show you in the next slide how you can justify May's conclusion. But just for now, that was his conclusion, that the central feature of the system is that large complex system exhibit a very sharp transition from stable to unstable behavior as complexity exceeds a critical value.
Alpha is the variance, yes?
Alpha is a variance, yes.
Because if it is just a parameter, it follows from dimensional analysis. Or like that, if alpha is not necessarily the variance, no, square root deviation. Yes. Okay.
Maybe. As I say, that kind of to analyze analytically this problem and to look at a real part of eigenvalues for real asymmetric matrices is a tough problem. And I don't think there were tools to study that problem in the 1970s. And this is what I want to explain.
Complexity is n in some sense.
Yeah, for Wigner, complexity was n, and his statement was that with exponentially, with probability exponentially close to 1, random system becomes unstable if n increases a certain critical value. That was his statement. Now, so that, as I said, random matrices, real random matrices with no symmetry assumed, asymmetric random matrices, are very tough to study analytically. And I think that Wigner, just one side remark, May in his Nature paper said that there is a paper by Genieber, but it's indirectly relevant. So he's aware about non-hermeticity, but somehow there are no details of his calculation, and there is no detail of his calculation in his book, which is very, very popular. So I don't know what the story is, but what I can kind of show you that the statement is true. But he didn't get the width of transition right. The width of transition relative width is 1 over square root n.
Sorry, is May, who is he? Is he physicist, mathematician?
Okay, Robert May is Australian, and he started as a theoretical physicist. He got interested in this. He was a theoretical physicist in Princeton, and he came with this idea. He was talking with psychologists. He came with this idea in Princeton. He published this paper. Was criticized by big shots in ecology, but some of them were more perceptive, to the point that he was actually offered a position in Princeton on the basis of that paper, which he declined. He went elsewhere, I can't remember where. Then he came back, and you might be surprised to know that he held an office of chief scientific advisor to UK British government. So he's a big shot.
Why surprised? He did another famous thing.
Which one?
Tell you.
Okay. Yeah, but he's famous. What he made his name, and he's famous for using methods of qualitative dynamical systems in ecology. Yes, right. So And there are still people saying that what he did was not exactly right and still arguing. But I don't want to argue, it's indirectly relevant to my talk anyway, because I want to consider a different model. Now, but coming back to matrices, and this is, will be important for me later on. So if we consider real random matrices of size n by n, then for complex matrices, Genieber in 1965 solved the ensemble exactly and 25 at 10. So he found eigenvalue densities and all eigenvalue correlation functions. But he didn't succeed in he tried, attempted to treat random real matrices, but he didn't succeed. And there had been no progress for real matrices until 1991, when Niels Lehmann and Hans-Jürgen Sommers published a paper in Fezerov letters where they actually derived the joint distribution of eigenvalues for real matrices. The difficulty there is that if you have a symmetric matrix with eigenvalues, and then complex eigenvalues come in pairs, and therefore the joint joint probability density function for eigenvalues will have to split into sectors where you have no real eigenvalues, one real eigenvalue, two real eigenvalues, and so on and so forth. And that makes treatment very complicated. So Lehmann and Sommers managed to derive this expression. It's a horrible expression. It's nowhere near, well, you can put it in a way which is similar to GUE, standard random matrix ensembles, but it's actually very difficult to treat. And Edelman actually rederived the expression later on in 1993, published in 1997. And Edelman was trying to his main object was to obtain the density or mean density of complex eigenvalues. And he succeeded it, but not actually using the joint density of eigenvalues. It's by a different trick, which I will explain later on. So Edelman found the density of complex eigenvalues, and looking at this density, so it's a standard form. There is an incomplete gamma function, which is more or less a partial exponential series, incomplete gamma function. And then what is characteristic here is that you have y in front of all these exponentials. So that
What is y?
Y is the imaginary part of z, and x is the real part of z. And because of that y, so you see that if you look at the density of eigenvalues, it is flat away from the real axis, but near the real axis it has a value. And therefore, even for finite matrix dimensions, you don't have rotational symmetry. So things are different away from the real axis, and they are and close to real axis. And this is a relevant observation. Then, in the limit of large matrix dimension, it's actually fairly easy task to do. In the leading order, the density of complex eigenvalues is constant, flat. So that what happens is that that value becomes more and more narrow, and in the limit it disappears. Now there is another interesting feature of this model is that you can also find the density of real eigenvalues, and that was accomplished by Edelman, Kost, and Schupp in 1994. And again, you can write down the explicit expression for finite n, then you can analyze it for large n. This term doesn't contribute, it's exponentially small, and this term is more or less the same as this one, and it gives you constant density in the limit of large matrix dimensions, but the interval here is from minus square root 10 to plus square root 10. So the expected number of real eigenvalues is square root n. So actually, random matrices with real random matrices exhibit this feature where you have accumulation of real eigenvalues along the real line. And this is will be very helpful for us later on. But for now, I just want to say that it still does not resolve, doesn't prove May-Wigner theorem, because there is no symmetry, and you can also look at eigenvalue counting measures, and you can prove weak convergence of eigenvalue counting measure in the limit of large matrix dimensions to uniform distribution
Is probability 1?
with probability 1 now. Yeah, it's taken a lot of time. It's actually very recent results, going back to 2010 or so. So it was 2010 by Tai Wu. So it took a Fields medalist to do it, more or less. So it was a long journey, but nowadays we can say that eigenvalue counting measure converges weakly with probability 1 to uniform distribution. It still does not prove Wigner theorem, because eigenvalue counting measure is not sensitive to individual eigenvalue. It does not track individual eigenvalues, it tracks macroscopic number of eigenvalues. But, of course, when May published his paper, there was some activity about how to prove it. And there was a paper by German in 1984 who proved that the spectral radius of random matrices, real random matrices, in the limit of large n is less than, properly rescaled, divided by square root n and by alpha, is less than 1. So in its own, German papers also doesn't resolve the problem, because there is this deep valley in the eigenvalue distribution. But combined, circular law combined with German paper gives you the answer. So kind of nowadays we can say that his theorem is proved, but it was a very, very long journey. Right, so I would also say that there was a recent paper by Ryder Sinclair, who actually improved a lot German's calculation. And for Gaussian matrices, they showed that they looked at the law of fluctuations of spectral radius around 1, and they found that that law is actually different for complex eigenvalues and for real eigenvalues details, and it kind of related to Gumbel distribution. Okay, so that's May-Wigner theorem, and it's kind of proof, more or less. And then kind of now we can say that linearized system is stable if complexity is small, and unstable if complexity is big. But this calculation is effectively neighborhood stability calculation. It does not give you any answer about what happens to system when they become unstable. All you can say is that when complexity increases, you get to the kind of the boundary of applicability of linear approximation, and that's all. So therefore, with Yan, we were thinking about how one can generalize this framework to nonlinear system, and what might happen to nonlinear systems when they lose stability. So that's a very long story about background to the little calculations that we did. Right, so in the spirit of May, we want to consider a very, very generic system, which probably has no relation to ecology. So we will not be claiming impact. But this is the system. We consider a system of n coupled differential equations, which have the same form as May system, except that a function f is now nonlinear, and we take it in this special form. So that it consists of two parts. One part is gradient or irrotational, and another part is solenoid dual. And for n equals 3, actually there is a theorem which says that under appropriate condition on f, you can decompose any field into these two parts. And for dimensions greater than 3, there are we cannot claim that you can represent any field in this form, because I think that there must be some kind of consideration about boundary conditions, but still it's a very generic problem. So and then for simplicity, again, we want to consider random systems, so we assume that f is a random field, and we endow this random field with kind of a measure by considering that v and a are independent, for simplicity, Gaussian fields, and that assumption is very essential for the possibility to do that calculation. We also assume that this random field is stationary and isotropic, so that it is a Gaussian field with mean zero. So then it's enough to specify the law of correlations. for this field. Kind of the matrix A is assumed antisymmetric. That's sort of in the spirit of this decomposition, Helmholtz decomposition. Now we want this function to describe the correlations between fields for any dimension n, and therefore you know that you can't just take a function at random and say it is a correlation function. It will have to be positive, semi-definite, at least, and so on and so forth. So if also you want that function to be correlation function for any dimension, then the choice is only kind of this one. So it will have to be Laplace transform of a measure of finite mass. So that defines the class of correlation functions we consider in our model. And we also assume that so there is a measure, spectral measure for V, for the field V. There is a spectral measure for the matrix field A. And these measures have kind of finite masses. And they also have finite second moments. And the finite second moment is important because then you can actually differentiate correlation functions, and also guarantee that the realization of random field are smooth, continuously differentiable. So that's more or less our assumptions on the system. So now that if you want to look at kind of stability property of the system, the first kind of question you ask yourself is that where are your equilibrium points? And that in such a generic setting, that's probably a very tough question to answer. But the kind of a simple question you may start with, you may ask how many points of equilibrium you actually have. That's a question that is amenable to analytic treatment. Right. So that's kind of the random variable we want to study. And this is the total number of equilibria points in this dynamical system. And when we say total, we mean the whole Rn. Okay? And we assume that this kind of rate of convergence back to equilibrium is non-zero, because the picture will be very different for mu equals 0. Right. So mu is positive. So of course, the points of equilibrium are just solution of these equations. It's very simple. And for now, I just want to formulate our conclusion, and then I will go and explain how we derived it. So I want to introduce one parameter, that's parameter tau. That's the second moment of spectral measure corresponding to V divided by the sum of second moments corresponding to vector field V and vector field A. So this kind of parameter in the system is actually measures interplay between gradient part and sinusoidal part. Okay, so obviously when tau is 1, then mu m squared A is 0. So we have purely gradient system. And if tau is 0, then f of x is purely sinusoidal. There is no potential part. Now, so the conclusion of our calculation is that to the leading order in the limit of large dimensions, not matrix dimensions, large dimensions, the average of the mean value of total number of equilibrium point is 1 if complexity mu, sorry, if mu is greater than mu critical, where mu critical, here is mu critical. Mu critical is just square root of 4 times number of degrees of freedom times kind of second derivatives of correlation functions. And then if mu is greater than 0 or less than mu critical, then actually you have exponential number of points of equilibrium. So there is a transition between in the behavior of total number of equilibrium points from having an average only 1 to having an average only exponentially many. And actually, if
the sigma total is positive, right? Because
sigma total is positive for yes,
small
sigma total is positive for m, and m. Did I put what is m?
Yeah.
M is mu divided by mu critical, so it's between 0 and 1. So sigma m is positive, and therefore you have. And when you approach 0 in little m, then you have a problem because it's kind of. Then you're back to a traditional question of random processes: how many crossing points you have for a field with independent entries. And there you have exponentially many on average, but in finite intervals. Here we claim that there are exponentially many, but not in finite interval. It's actually in the whole space. Right, and also we can say that the crossover region is 1 divided by square root n, relative. And then we can also write down the crossover profile for this average value. So indeed, kind of similarly to May, we can say that as the complexity exceeds a critical level, the large complex and linear systems exhibit a sharp transition from having an average 1 point of equilibrium to having on average exponentially many points of equilibrium. Now, if you look at this equation and you kind of try to analyze it, then you'll see that with probability close to 1, it will always have at least 1 point of equilibrium. So actually what this statement says is that in the limit, so this is, you should interpret this statement as a kind of limiting transition. So in the limit, the total number of eigenvalues is 1. But it also, if in addition, if you know that you always have at least 1 point of equilibrium, then you can say that in probability, the total number converges to 1. So we don't know how to do kind of analysis of fluctuations in the critical area. Okay, so that's
Even just know that they are small, not novel, just self-averaging property, no?
we don't
Not
have.
without the rate, just
We don't know. I'll show you where kind of where it breaks for second moments. Yeah, maybe there are other ways, but the kind of our
Recently there was, okay, not on
Yeah.
this problem, but on a related problem, there were calculations by Subag, who calculated something related to second moment of this quantity for a related case, but not for covered
my
by.
point is that to prove the law of large numbers strong,
Yes.
you need not to know the second moment, in principle. Ergodic theorem doesn't require, so maybe.
Some other, no, yes, maybe there are some. But
But
I just want to mention that in
Yeah,
principle,
yeah.
one can get something about second moment, very recent work.
But I also want
we
to
don't
add
know.
on this note that kind of if mu is 0, then actually fluctuations are also exponential. That's more or less known. It's very bad situation. Okay.
Do you know anything about stability? How stable are these stable points? What
I will towards the end I will answer your
Okay.
question
Partly.
partly. Actually, Yan is a better position to answer, but I will say something about it. Right. So that this is how we do this calculation. It's actually a very nice and neat calculation. So if you want to count the number of zeros of this function, so the best way is to employ the Katz-Rice formula
Of Gaussian function.
of Gaussian function. Yeah. For Gaussian function, the best way is to employ Katz-Rice. And the Katz-Rice is a very simple formula because you approximate this delta function by a step function, for example, a very smooth function. And then you're left with kind of, in one dimension, you just have a kind of linear approximation near 0. And this determinant or a modulus of derivative comes from just changing variables. So it's a simple formula. And stationarity and Gaussianity actually in this setting imply that the field itself is independent of its derivatives. And that's very, very crucial kind of a fact for our calculation. So of course it is independent, it is uncorrelated because of stationarity, and it is independent because of Gaussianity. Right, so then what you do when you take the average of n total, you actually see that you can split it in kind of a product of two averages. And taking the average over realization of f and integrating over the whole space, you just get a constant, 1 over mu to power n. It's a simple calculation. And then you're left with just averaging the Jacobian, more or less. And now stationarity means that you don't have a dependence on x. And the integral of dx is taken care of by this delta function. So that the conclusion of this little calculation is that actually n total is just an average of the spectral determinant, where J is just Jacobian of a vector field F with respect to axis. Now, so here we come to another calculation, which is pretty simple. It's tedious, but simple. So you have a Gaussian random field. You know its correlations, and you just take derivatives. You also can calculate correlations of derivatives. And at the end, this is the answer. So Jij is the derivative of Fi with respect to Xj. And then we have to look at the law of correlations between matrix entries. And this calculation actually gives a well-defined answer, which contains two parts. Which contains two parts. So I start with this part. This is just, it arises from diagonal elements. So this is just the law of correlations of diagonal elements. And this part corresponds to what is known as elliptic Ginibar ensemble. So the one that I showed you before, except that the one I showed you were matrices with no correlations between matrix entries. But you can also consider an ensemble of random matrices, real matrices, where you have correlations among matrix-centric, symmetric with respect to the main diagonal. So if you do this, then that's the law of distribution. It contains this parameter tau. So that all in all, you can decompose matrix J in two parts. One will be Ginibar real elliptic matrices following this distribution. And another one is just identity matrix with random amplitude T, which is normal. So that again, J from this calculation is simply alpha times x, where alpha is related to kind of second moments of those spectral measures, minus T times I, where T is independent of J. So that plugging it back to this formula, you arrive at this expression, and also rescaling T with n. So that's the problem that if you want to know the total number of stationary points, that this is the integral you would like to evaluate in the limit of large n. Right, so as some of you know, actually finding the problem here is actually having this absolute value. That's more or less a killer in kind of random matrices. It's very difficult to deal with. If you don't have absolute value of determinants, then you can take averages. There are formulas kind of give you the answer. And also, as Yan knows, if you kind of even apply supersymmetric technique, it's not that simple. So in a way, in this situation, we are lucky because we can reduce this problem to another random matrix problem, which takes care of everything more or less. But kind of my point here is that there is a very challenging, interesting analytic problem to work with averages of absolute value of characteristic polynomials of random matrices, finding their correlation functions, and so on and so forth. And in this community, there will be similar problem for kind of Schrödinger operators. And Yan can probably tell you that those type of objects arise in a very similar setting.
In fact,
We already discussed.
Here we try to do.
Yeah. Right, okay, so I will move on and just show you the trick, how to reduce this seemingly untractable problem to a tractable problem. And I go back to kind of a paper I showed you, Edelman, Costa, and Schuh. And in 1994, they were also thinking about how to prove Lehmann and Sommer's conjecture that the average number of real eigenvalues in random matrices behaves like square root n. And that was pretty clear from kind of joint density of eigenvalues that was produced by Lehmann and Zomers, is that kind of it's very difficult analytic problem. So they came up with a little trick which actually helps to solve this problem analytically. So instead of normally in random matrices, if you want to find the kind of law of correlations of eigenvalues, you diagonalize matrix by unitary transformations, you integrate additional degrees of freedom, and then you're left with the law of probability density law for joint distribution of eigenvalues. But in this setting, actually it pays off if you do not diagonalize matrix, but you just do it first step. Instead of reducing matrix to for non-Hermitian matrices, kind of an analog of diagonalization is reducing it to Schur form, upper triangular form. And it's still kind of difficult. You can write down expression for joint density of eigenvalues, but it's not helpful. Nowadays we know how to deal with it, but it's not helpful. So instead that you just do the first step by the help of householder reflection, that's just a transformation that kind of exchanges eigenvector and a basis vector. And then you can explicitly write it down in terms of eigenvector. And what this, it's a unitary transformation. So you have a change of variables. The Jacobian of this change of variable, it's fairly straightforward to calculate it. The Jacobian is this just the spectral determinant. And then if you look at this matrix measure, you will see that kind of when you substitute that household transformations into quadratic form here, the household transformation disappear. So actually, you do not need to integrate over them. So therefore, the conclusion is that if you want to find the density of real eigenvalues of a matrix, you what it is, mean density. It's sum of delta functions. You average. You look at just one eigenvalue at point x. If you know that there is an eigenvalue at point x, then you do this trick, and then you arrive at the relation between spectral determinants and the density of real eigenvalues. There is a similar relation between complex eigenvalues and spectral determinants. The only difference is that you have absolute value squared here. And that is the way how Edelman proved his version of Sokolov. Right, so now the problem becomes more tractable, because actually you reduce this the spectral determinant to density of real eigenvalues, and there are some expressions for density of real eigenvalues. So that's kind of the formula that we arrived at. It expresses the average number of the average total number of points of equilibrium in nonlinear dynamical system through the density of real eigenvalues in an elliptic ensemble of random matrices. Now, of course, kind of this is still evaluating this density is still a challenging problem, but there has been a lot of progress in the last 10 years about how you can write down eigenvalue correlations and also densities starting from the joint distribution of eigenvalues. And it's very similar in a way to kind of GUE techniques, except that you do not have orthogonal polynomials, you have certain skew orthogonal polynomials, and actually even the task of finding those skew orthogonal polynomials in explicit form is quite a challenging task. But we were lucky with Yan, because Forrester and Nagao did this calculation for elliptic matrices, and they represented, they found that the density of real eigenvalues for finite matrix dimension consists of two parts. Their structure is very similar to the one I showed you for circular ensemble, except that except that powers of x are replaced by rescaled Hermite polynomials at point x. But otherwise, the structure is very similar. And then in the large n limit, this term here, the first term actually converges to a constant, and it gives you density, and the second term, this one, exponentially decays. Okay, so now the form of this expression is very suggestive how you want to treat it analytically. So you just try to use the Laplace method, and if you try to use the Laplace method, you will see that actually in the above the critical region, this is not enough. So you also need to know how the density of real eigenvalues decays exponentially outside the support of distribution of eigenvalues. But this can be done. It's a nice little problem. And we can express this density, the tail, in this kind of form, large deviation form. And I don't write down the expressions. And the rest is just a straightforward application of the Laplace method, which gives you this answer. So that coming back to the question about fluctuations, I think that we used heavily that derivatives of a random field for Gaussian stationary field are independent of field itself. And if you look now at second modes, it's kind of very difficult to see how you go about decoupling. So maybe it's possible, and as Yan says, there are other techniques, but at the moment we don't know. Now, so also, if you look at this kind of term and see how it behaves near criticality point, where mu is mu divided by mu critical, then you'll see that it kind of decays as 1 minus m squared, so it is suggestive of kind of the width of the critical region, and actually kind of by pushing this calculation you can find the profile of average number of total points of equilibrium in the transitional region between situation when you have one equilibrium point on average to situation when you have exponentially many points. And as usual, kind of in random matrix calculation, normally this would be a very universal expression. And we expect that it's kind of universal and it applies to other nonlinear systems. Yes.
So in none of your formula, it looks like one can take tau to 1. I mean, something happens. What happens? In that limit?
When tau is 1, we are back to gradient fields. So it means that
Or was this formula sick when it
this is kind of, there is no uniformity in tau. There is no uniformity in tau because for when tau is 1, you have gradient fields. Actually, kind of there is a similar phenomenon there, but the sigma is different. And actually, I will show in 2 slides. I will show it. Right. So this is a calculation, and we expect this transition to be a fairly generic one. Of course, we chose a very simplistic model, which was amenable to analytic treatment. But there is a paper which we didn't know at the time, which sort of treats a very similar, not very similar, but also a system non-linear PDEs in the context of neural networks. So it was done by Weinreib and Tubal. And they considered, so this is also a nonlinear system. J's are ID variables, and sigma.
I and J in the X point.
Oh, that's a misprint. This should be I. Should be. Where kind of, it's a different structure, but they assume that again the field is 0 on average, mean value 0, and has finite second moments, and kind of using various approximations, which I should say that at least one of them I can't see how to control, but they arrive at a very similar conclusion that there is this transition between a situation, stable situation when you have in this system, when you have an average 1 point of equilibrium, to a situation where you have exponentially many points of equilibrium. They can only do perturbative analysis, but anyway, the conclusion is very similar. It is a very different system. So we conjecture that, or presume that this phenomenon, explosion, or as Yan says, detrivialization of geometry is a very generic one. And it would be interesting to kind of study other problems, other models to establish this type of transitions. Now, I just want to conclude this presentation with a list of open problems. So the biggest one is what we calculated. We calculated average values, and we can say something about fluctuations in the regime when the situation is stable. But at the moment, we can't say that much about magnitude of fluctuations of n total in the critical regime. And of course, if fluctuations are very big, then mean value does not, average value doesn't give you any kind of answer.
But this is not the case. No, we know
It's not
that
the
this is
case.
not the case from some numerical simulations, but
mathematical,
how to prove it?
mathematical, it's very interesting and challenging problem. So second question is actually kind of the first step is to look at the total number of eigenvalues, total number of stability, total number of equilibrium points. But then of course you start asking questions how you classify those points, and which of those points are stable, which of those points are stable, and in n dimensions there is a whole zoo of kind of stability patterns. And in this generality, we don't know the answer. It's a challenging problem. And but Yan and Celine Nadal, they actually treated this kind of the same dynamical system from a different point of view, but only for potential fields. And this is where you have symmetric matrices. And in that setting, they actually found that kind of unstable equilibrium points dominate. So there are, even on exponential scale, there are many more unstable points compared to stable points. So interestingly, their calculation gives an expression for the total number of points of stable points in terms of the largest, the distribution of the largest eigenvalue of symmetric Gaussian matrices. So it is plausible that a very similar calculation can be done there, but it's kind of not a straightforward generalization. So I think that again we have another projection that kind of the number of stable equilibria will be related to the distribution of largest real eigenvalue in elliptic ensemble. But at the moment, we don't know how to prove it. And I think that there are other interesting problems, for example, which are amenable. You can probably do it. For example, we started with a model where all n degrees of freedom have the same relaxation scale to equilibrium. And this rarely happens. So you actually can consider a model where you have different relaxation times. And again, kind of what is analytical treatment? It's not a simple generalization, but it should be possible to do it. And of course, another mathematical problem is that how you extend that calculation beyond Gaussian case. But I presume that one is very, very difficult. So that's all I wanted to tell you. And thank you.
Thank you very much. Questions?
Okay. Remember in statistical mechanics, whether you try to compute the log n, not n itself, but log n, because it could be self-averaging. No? Have you tried?
No, we haven't.
No hope.
No hope?
No.
No, okay. But
No, I mean, with the existing methods, no hope. But who knows, maybe some other method.
We need some creative ideas
Yes.
how to treat it.
With
For
this
example,
method,
to
it's
prove
pointless.
asymptotic additivity in n, and you get ergodic theorem, like in spin glasses.
Yeah, maybe it's
Yes.
yeah.
It's very close to spin glass problems, yes.
Of course. No, no,
People
it's-
discuss it actively. What I mentioned, this calculation of second moment, is in spin glass context.
I understand, but
Yeah.
nevertheless, but if the spin glasses are replicas, we can see there is an enormous amount of things that could happen. Yeah.
Probably something of this happens.
Other questions?
It's like Sherrington-Kirkpatrick. It seems like Sherrington-Kirkpatrick for an analog.
To some.
Okay, let us thank the speaker again. So let's make a 5 minutes